I mentioned this before, how to check two solutions are linearly independent. Yeah, here we have the, specific way. So after you do the calculation, you can see if they are linearly independent or not. Yeah. All right. So here we need to use some, fourth student. We need, two more. Oh, 5 students. All right. Let's look at the linear independence. Should be here. Yeah. All right. Yeah. So recall the original question from homogeneous second-order linear ODEs. Yeah. When we try to find a general solution, we need to find a basis. Yeah. So we need to get a y1, y2, two solutions. But after we get a y1, y2, how do we know they are linearly independent? If they are not, then you cannot use them to represent a general solution. Yeah. Because if you do not use two basis functions, you cannot cover all the general solution. Okay? Yeah. So we need some method to tell us how to determine if they are linearly independent. Okay? Yeah. Under what condition that y1, y2 are linearly, I need to use this one. y1, y2 are linearly independent on an open interval I. Yeah. Open interval I. Okay? Yeah. So we do not specify how large is that I, just some interval I. Okay? Yeah. Interpretation. Let's try to understand the exact meaning of linear independence. Yeah. We call y1 and y2 linearly independent on I if the equation, here, be careful here. Equation is simple, but when you understand there is some subtle thing you need to get. K1, Y1 is a function of X. Yeah. Remember, there is here it's a function. Yeah. Plus K2, Y2 function. And this equation should be true on interval I, on I. Yeah. So if it is true, that implies that K1 equals 0, K2 equals 0. Yeah, that's the exact meaning of linear independence. Yeah, linearly independent. Yeah, yeah. Try to understand this. Okay. Yeah. So let me repeat it. This condition. All right. We start with this equation. Assume two constant K1, K2. Yeah. Arbitrary constant K1, K2. Okay? Yeah. If those two constants can make these two functions y1, y2 satisfy this equality on the whole interval I. Okay? On the whole interval I. Yeah. Everywhere. X, you can take X everywhere on this interval I. Yeah. Not just the one X, okay? All X on interval I. Yeah. All right. If you have that, then it implies that K1 must be 0 and K2 must be 0. That's the meaning of linear independence. Yeah. if you can find K1, K2, one of them non-zero, usually both non-zero, such that K1 times Y1 plus K2 times Y2 not equal to 0 for only one point on I, then you destroy the whole condition. Okay? So if you destroy the whole condition, they are not linearly independent. The opposite, they are linearly dependent. Try to understand this. A little confusing, but try your best to understand. All right. That's our starting point. We start from this condition. Then we do some, deduction. All right. Because, all right, so let's assume this is correct. Okay, this is correct. All right. This is correct. The whole function, if you look at the left-hand side, that is a function, right? Yeah. That is a differentiable function, right? Yeah. Y1 solution, Y2 solution, they're both differentiable. Okay. So the left-hand side, actually, it is a differentiable function. If it is a differentiable function, we can take derivative. Yeah. So let's take derivative of both sides, also 0, right? Yeah. 0, both sides, the function value equals 0. Then you take derivative, also 0. Okay, no problem. Yeah, let's do it. Okay, after we apply derivative, we get second equation. Here, you can see when we apply derivative, we can get a completely new equation. How about that? That's a new equation. So we can take advantage because we have a new equation. All right. Now we have two equations. Yeah. Two equations important. Why? Because there are two unknowns, K1, K2. Here we treat K1, K2, both unknowns. In order to determine two unknowns, do we need two completely different equations? Yes. So here when we start, we only have one equation, but after we take derivative, we get a second, quite different equation. The property, completely different equation. Now, these two equations sufficient to determine K1, K2. So the next step, let's write two equations as a linear system. Here, okay? Linear system. Linear algebra a little bit. Here we use the linear algebra language a little bit. Okay? Yeah. Very simple way to use linear algebra. So we write, this is a homogeneous linear system, right? Homogeneous. No, right-hand side is 0, all 0. So that's homogeneous. Left-hand side, linear equations. Okay? All right. Can we write it as this matrix form? Matrix form. Think about that. Okay? Matrix form. Yeah. 2 by 2 matrix. This is a vector, dimension 2 vector, K1, K2. Yeah. 2 by 2 matrix multiplies a vector equals 0. What condition? Under what condition? Yeah. All right, so here, there is a theory in linear algebra. So here we need to use that. Theory in linear algebra. Homogeneous linear system. Now let me give you that result. We need to apply it. Here, we have a homogeneous linear system. Yeah. And Look at that. So here, the conclusion is K1, K2 must be 0. K1, K2 must be 0. K1, K2 must be 0. Yeah. Because in this linear system, when K1, K2 equals 0, we call it trivial solution. Trivial solution. Yeah. Yeah. Both variables, unknowns, we treat as variables. Both unknowns, variables equal 0, that's the trivial solution. Okay? Yeah. We can see from this system, we know this linear system always has trivial solution, right? Always. When you plug in K1, 0, K2, it's always true, right? Yeah. So we say a homogeneous linear system always has a trivial solution, or the trivial. Trivial solution only one, okay? All zeros. So the homogeneous linear system always has the trivial solution. Okay, yeah. That's simple. Yeah. Second thing is, the question we want to ask, is it possible that homogeneous linear system does not have a, is it possible that a homogeneous linear system has a non-trivial solution? That question. Homogeneous linear system has a non-trivial solution. Is it possible? Yes, it's possible. Okay? Homogeneous, it's possible for a homogeneous system to have a non-trivial solution, but you need to check condition determinant of its coefficient matrix, 2 by 2. Okay? You need to calculate a determinant of its coefficient matrix. Determinant. You know determinant, right? 2 by 2 determinant. Okay? The formula. Yeah, we will see. See it soon. Determinant. All right. You need to calculate the determinant of the 2 by 2 coefficient matrix. If the determinant equals 0, then the homogeneous linear system has a non-trivial solution. If the determinant does not equal to 0, then the homogeneous system does not have any non-trivial solution. That's the result from linear algebra. Okay, we need to use this result here to check the linear independence. Yeah, so let me repeat that. Okay, all right. We know any linear homogeneous system must have the trivial solution. But we do not know if it has a non-trivial solution or not. So how to see if it has a non-trivial solution? We need to calculate the determinant of its coefficient matrix. Yeah. Yeah. Now, based on the determinant value, we have this conclusion. All right. After we calculate its determinant, if it is 0, then our conclusion is this homogeneous linear system must have a non-trivial solution. Okay? So that's the 0 case. Yeah. If it is non-zero, then this linear homogeneous system does not have any non-trivial solution. Okay? That's the whole result we need to use from linear algebra for this problem. Okay? All right. So let's apply it. Apply it. All right. Now, we calculate the determinant. Yeah. So we use this, vertical bar, like absolute value. Bigger absolute value, this notation. So we calculate. And here, because we want to check linearly independent condition. How to get a linearly independent condition? Okay? We like to see the determinant of its coefficient matrix not equal to 0. Okay? If it's not equal to 0, then by the result I mentioned from linear algebra, it has no non-trivial solution. So the only solution it has must be trivial, right? Must be trivial. So what do you mean trivial? K1 equals 0, K2 equals 0. That's what we need to have, okay? So consider this whole logic, okay? Not too complicated, yeah. But you need to have a good understanding, yeah, yeah. All right. Because later when we summarize the whole result, we, a lot of details. Yeah. We need to pay attention, yeah. All right. The only solution is the trivial solution. Yeah. If we have the condition, determinant is non-zero. Okay? All right. Yeah. Yeah. From there, then we need to write everything out. Yeah. All right. This time we look at both linear dependence and the linear independence. Yeah. And we look at the determinant, we give it a name, Wronskian, okay? That Wronskian. So the determinant value, expression, yeah. So we calculate that determinant. Yeah. So define Wronskian in this way, yeah, W notation, Y1, Y2, that's our formula for the determinant. The specific formula for the determinant, y1 times y2 prime minus y2 times y1 prime. Okay? Yeah. All right. Yeah, so now we try to, look at the whole picture. Yeah. Now we apply the result we just developed. So here, but we need to look at the whole picture, covering both linear dependence and the linear independence. Yeah, these two things. All right. Yeah, so on open interval I, this is, the ODE homogeneous second order. Then, here, this result only true for second order homogeneous ODE. Okay, so you cannot generalize. If you generalize, higher order, first order different, second order. Okay, when two solutions y1, y2 on I are linearly dependent, the first time dependent on I. Okay, let's look at dependent on I. If and only if their Wronskian is 0 at some x0 in I. Yeah. So here you can see for linearly dependent, you only need to find one point in I, its Wronskian equals 0. Only 1 point. Okay? Yeah. Yeah. So not all points. Okay? Yeah. Only 1 point. It's enough to tell you y1, y2 are linearly dependent. Yeah. Okay? Yeah, pay attention to this detail condition. Okay? All right. Furthermore, if W equals 0 at an x 1 point, still 1 point in I, then look at 1 point would guarantee y equals 0 on the whole interval. How about that? Okay? Yeah. When you check condition, you only need to find 1 point in I such that W equals 0. But if you have it, then it implies W equals 0 on the whole interval. How interesting. Yeah. 1 point can force the whole W function. W is a function. Okay? That W function must be identical to 0 on I everywhere. Okay? That's interesting. Okay? Yeah. So that is one result. All right. Hence, if there is a x1 in I at which w not equal to 0. Yeah. 1 point on I, w not equal to 0, then y1, y2 are linearly independent on I. Okay? See? When we check independence, we only need to check 1 point. Yeah? 1 point. Yeah. The previous slide, when we do discussion, we do not work on 1 point, right? We look at all points. Yeah. But here, because after we do the discussion here, actually the results I put here containing several theorems in the textbook. Several theorems. Yeah. So we can prove. These results can be proved easily. Yeah. Yeah. All right. So the second one. If w not equal to 0 at one of the points in I, then it's enough. You can say y1, y2 are linearly independent on I. Okay? Yeah. Here I spend a lot of time talking about the details. Then you can expect you will get many concept questions from this one. Okay? Yeah, concept question. Yeah, I ask you about the details. So 1 point, all points, 0, non-zero, trivial solution, non-trivial solution. Yeah, that kind of thing. Okay? Yeah. All right. Yeah, so we finish this topic. Okay, yeah. All right. Example. Yeah, here, a simple example. Yeah. Now we can go back to check. Yeah. Because we look at this homogeneous second order linear equation with constant coefficient. So we know its solution, y1, y2 easily. Yeah? Yeah. So we know e to the x, the first solution. X times e to the x is second solution. y1, y2. Now let's calculate its Wronskian. Yeah. Then determinant. Yeah. The formula, cross product, take difference, cross product first, then take the difference. Okay? All right. Then cancellation and factorization, e to the 2x, definitely not equal to 0. Okay? This function can never be 0. Yeah? Linearly independent. These two conclusion is these two functions are linearly independent. That's simple, right? Yeah. So now, here, I need to, because I want to minimize it. Yeah. Right. Minimize it. Yeah, because it will be in the video. Yeah. Oh. Yeah, Andy, right. Yeah, but on my screen I minimized. Oh, I also need to minimize there. Yeah. 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 All right. Okay. Yeah. Yeah. All right. Linearly conclusion independent, and we complete the whole topic. All right, so let me jump to part C, our new topic today. All right. Yeah. Part C, modeling of free oscillations and forced oscillations. Two types of oscillation. oscillations. So now we need to look at the application questions for this part. Yeah. All right. C.1, mechanical mass spring system. Yeah. Setting up the model. Yeah. Let's look at the model. Yeah. So in middle school, probably you saw this system before. Yeah. I remember I learned this topic in middle school. Yeah. Junior, yeah. High. Yeah. All right. So this is a typical mechanical mass spring system. Yeah. At the beginning, yeah. So we have a spring like that, no weight. Yeah. Then we put a iron ball below, so there is a weight for this iron ball. Yeah. So stretched certain displacement, S0, yeah, stretched there. Okay, all right. Then we can, put a force on it, on the system. Force, apply some force on it. All right. So here the spring, an ordinary coil spring that resists extension as well as compression. Yeah. Yeah. Two directions. Yeah. Extension, because the force has direction. Force has direction. Okay. Extension, yeah, the force is one direction, because if you stretch it downward, there is a force, pull force, opposite direction. Okay? Yeah. If you compress it upward, then there is a force downward, yeah, opposite direction. Yeah. So that's the typical property. Restoring force. Yeah. So that force generated by the spring, yeah, we call the restoring force, by Hooke's law. Hooke's law telling us some property about the restoring force. F1 equals minus ky, negative k times y. Okay? Yeah. Y negative, opposite direction. Okay? K is a positive constant. K is a positive constant. Okay? Opposite direction with respect to y. Y is the displacement. Displacement has a direction. Yeah. Yeah. All right. So here we used downward as the positive direction. Yeah. Downward as the positive direction. Okay. Where K is the spring constant with K positive value. All right. And from Hooke's law, yeah, and based on our intuition, the stiffer the spring, the larger the K value. Yeah. The stiffer, yeah. Because the stiffer, then K times Y, the force is larger. When the force is larger, K is larger, right? Yeah. All right. And this is the direction. Yeah. This arrow tells us, yeah, two directions, both positive direction for force, and displacement. Yeah. All right. So with the basic information, now we can study the motion of the ball, spring, mass spring system. Force from the weight of the ball. Yeah, because this ball has a weight. That weight can generate force by gravity. Yeah, that's the gravity part. Yeah. Gravity force. Yeah. So that force, we use F0, negative F0 equals m times g. The mass times g, gravity constant, yeah. Opposite direction of the yeah, right, yeah, all right. The constant of gravity here, I use 9.8 m per s squared. Yeah, this unit. Yeah, I didn't use that feet. Yeah, there is another one, 30 something. Yeah, yeah, right. Yeah, because yeah. So if you use feet, so all the unit everywhere you need to use feet. Okay. Yeah. So if you use meter, so everywhere we use meters. Yeah. All right. F0, but for the whole system, although this F0 equals that, yeah. But in the whole system, we know that ball stays there in the system all the time, right? Yeah. So up and down, apply the force, always there. Yeah. Then it's like neutral. Neutral. Yeah. It's rho because it's always there. Okay? Always there. Yeah. We do not remove it. Yeah. We always keep that F0 there. Yeah. So no effect on motion because it is in equilibrium with the weight W of the ball. Okay? From beginning to end, it's always there. Okay? There is no change. Yeah. So we include it in the system. Yeah. So it's in the system. And there is no change, no force change. Yeah. So it's just like nothing. Yeah. No effect, right? No effect. Yeah. So that's this F0. Then, Newton's second law. Yeah. Because the Hooke's law only applies on the spring part. Okay? Yeah. Other than the spring, we have other things, right? Yeah. Outside, several other things. Yeah. So we need to apply Newton's second law on the whole system. Yeah. More than just the mass spring system. Yeah. Because we have other forces. Yeah. So Newton's second law, we have this formula, mass times acceleration. Oh, that one. All right. That is m times y double prime acceleration. Okay, double prime equals force. Yeah. So now you need to look at this force part. Force. All possible forces, right? Yeah. Not just the one. Yeah. You have four forces from, different sources. Yeah. All right. The force is the resultant of all the forces acting on the ball. Okay. Later, we will add one by one. Okay. At the beginning, we try to simplify it. Yeah. Later, so we consider various sort of forces on the system. Yeah. All right. So now it's enough. So we can set up differential equations. Yeah. All right. ODE of the first type, the simplest type, undamped system. Undamped system. Okay? Yeah. The simplest, we make assumption. Yeah. All right. So look at this system. Yeah. Yeah. First, based on our intuition, every real world such system cannot be undamped. Okay? Cannot be completely 100% undamped. Yeah. Yeah. Because there is some force, will, slow down the motion, right? Slow down the motion. There is some tiny force, even, by air, can slow down the motion. So it cannot be treated as completely undamped system. Yeah. But in order to consider that undamped, we need to do approximation. Yeah. Approximation. So we use two conditions to allow us to approximate undamped system. Yeah. Yeah. Otherwise, if these two conditions are not true, then the approximation would be very poor. Okay? Yeah. If the two conditions follow well, yeah, then the approximation pretty good. Yeah. The first condition, the damping is small. Yeah. Damping is small. Okay, the force causing the damping is small. All right. Second, the motion of the system is considered over a relatively short time. Yeah, short time. Yeah, not too long. Yeah, the longer the worse. Okay, the longer the approximation would not be accurate. Yeah, so not that close. Yeah, all right. Now, our first simplified problem by Newton's second law and Hooke's law. Both. We can set up differential, second order differential equation like this. All right. Yeah. M double prime. Yeah. All right. From Hooke's law. From Newton. All right. From Newton's law, second law, Hooke's law. Yeah. Yeah. And damping part, small. Damping part, later we will see. Yeah. Damping part here, because there is a term for the damping part, we treat damping part as 0. So here you cannot see the damping part. It's 0. Yeah. Yeah. All right. So that's the simple equation. That's the simple equation. Okay? Yeah. Yeah. Only, yeah, because by Hooke's law, the spring has a force, restoring force, right? That restoring force generates the motion my double prime. That's for the motion part, right? Yeah. Mass times acceleration. That's the motion description. Okay? So the spring's restoring force causes the whole motion. Now, only one force, spring's restoring force, that causes the motion. Yeah? So we get this equation. All right. Next, we want to solve it. Okay? Yeah. We did it before. We have formulas. Yeah. Here we just apply the formulas. Yeah. Yeah. So let's recall the formula. Standard form. Yeah. We did it before. I just copied our old formulas here. We apply it. Yeah. Because we consider this general standard form before, and we solve it in 3 cases. Yeah. Here we do the same thing here. Yeah. We do, because our current case is one of the 3 cases. All right. Standard form, let's convert it to the standard form. Yeah. Divide the mass and number both sides. That's the standard form. Okay? Yeah. In the standard form, A equals 0. Yeah, we don't have the middle term, A times Y prime. So A equals 0, B equals K over M. Very simple equation. Yeah. All right. Then, which of the 3 cases do we have here? We calculate the discriminant. Yeah. So last time I mentioned this word discriminant. Yeah. So then I go back and check. Yeah. It's called discriminant. Yeah. All right? Yeah. So let's calculate the discriminant. It is defined as b squared minus 4b for this particular equation. B squared minus 4b, but a squared minus 4b, but a is 0. A is 0, so the discriminant becomes minus negative 4k over m. So it's a negative number. When the discriminant is a negative number, then that's our case number 3. So, case number 3. So we apply the solution for case number 3. What's that? So I copy the solution for case 3. y1 equals this function, y2 equals that function. But in our case, our a equals 0, so e part is gone. Because e to the 0, it's 1. So e part is gone. So we only have cosine omega x and a sine omega x. But we need to find the omega, because omega, here I use 0. I use 0 for this omega. All right. So that is the omega number, root of k over m. K over m, square root. Omega 0. So then we can write the general solution immediately. Capital A constant times cosine omega 0 t plus another constant, capital B, times sine of omega 0 t. That's the general solution for that problem. Okay? After that, then we have some concepts. After we get the general solution, one is the period. We can calculate the period because this is a periodic function. Y function, our solution is a periodic function. We want to see how large is its period. Okay? So here, let me calculate it. The answer is 2 pi over omega 0, the period expression. But I want to explain why. Why? So look at that. Look at the first equality. Let me cover the second. For the first equality, cosine omega 0 t equals cosine omega 0 t plus 2 pi. Because cosine is a 2 pi periodic function. The period of cosine, it's 2 pi. Okay? 2 pi. The whole circle. 2 pi. All right. Now, starting from there, when we, let's use this 2 pi, adding 2 pi, the same value. Now let's factor out that omega 0 out of the parenthesis. Inside parenthesis, t times 2 pi over omega 0. Now you can see the meaning of the new period, because when t is the variable, okay? Omega 0, that's the constant part. When we look at the variable part, when this variable add a small constant value, 2 pi over omega 0, the whole function is the same as before, no change. Based on that observation, can we say this number is the new period? Right? You add that constant number on top of the variable, you get the same value. Can we treat it as a period? That's the definition of the period, right? What's the definition of the period? Think about that. Here, let me write the definition. If you want to understand. So why we say this is the period? Definition of the period. Let me use f of x. X plus t equals f of x. Okay? That capital T we treat as a period. Okay? Because your f plus t, but that x should be true for all x in the domain. Okay? For all x in the domain, you have that relationship. Okay? Plus t. So that t we treat as the period. All right? And by the definition of the period there, x here we use t. T the same as the x. Little t plus this number corresponds to the capital T there. Okay? The period, capital T there. All right? So that's why we treat it as the new period by definition. Okay? Yeah. All right. Yeah. Because why I spend time talking about the period? Because in the real world, when you solve an engineering problem, then you need to do interpretation. Some period, the frequency. After you get a period, then we calculate the frequency. That's just the reciprocal of the period. Okay? How do you calculate the frequency? 1 over that period number, reciprocal of the frequency, you know, it's an important concept in engineering problems. Yeah. So we need to calculate the frequency. That's, you know, reciprocal of the period number. Omega 0 over 2 pi. Okay? All right. Yeah. So here we also call this natural frequency of the system, of this mass spring system. Natural frequency. Okay? Yeah. 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 The definition. Yeah. Because you may have other different frequency, right? This is natural frequency. Later, yeah. Why? So here we give a natural frequency because probably you have other different frequency, different types of frequency. Yeah. Think about when we apply force, external force. Later you will see we will apply external force on the system. That external force has its own frequency. How about that? That frequency is different from this natural frequency. 2 different frequencies. Okay? This one is natural. That one is, you know, external, you know, frequency. Yeah. Yeah. All right? Yeah. Okay. All right. So we finish this first. Simplest case for the system. Second, this time ODE of the damped system. Now we need to consider, you know, damping force. Yeah. Damping force. We will add a damping force into it. Yeah. All right. So this time, how to simulate that damping part? Here you can see, you know, some little device added, you know, dashboard, you know, just some force slow down its motion. Okay, the damping part, simulation part. Yeah. Yeah. All right, add a damping force this time. Yeah. Yeah. So we introduce a new force number F2. F2. The damping force has this property, okay, equals negative constant C. So that C to be determined, yeah, that constant C times y prime. Y prime is the velocity of this ball, okay, yeah. Y is the displacement function, okay, yeah, displacement function. Its derivative, the velocity of the ball. Now you can see, when you apply the damping force, slow down the velocity. How about that? Okay? Yeah. Because the negative, you apply it in the opposite direction of the motion. Okay? Yeah. 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 All right. So negative C times y prime. Yeah. C, the damping constant. Yeah. All right. We assume this damping force to be proportional to the velocity. It's a good approximation for small velocities. Large, it's not good. The approximation, not that good. Yeah. Small, you know, good, yeah, good enough. Yeah. All right. ODE of the damped mass spring system. This time we need to look at a, you know, modified, yeah, different from our previous one, because we add a damping force term. You can see the term in the middle, Cy prime, is added. Yeah. That force, yeah, added. So we have this 3-term, yeah, second order, homogeneous equation. Homogeneous, another property, with constant coefficients. all coefficients are constant coefficients. Yeah. So we have the solution formulas. Yeah. All right. Standard form, yeah. AB, yeah. We studied the standard form before. Yeah. AB, yeah. Here we apply the standard form. Then we need to look at its characteristic equation, lambda square. Yeah. This lambda characteristic equation. Then we look at the discriminant. Yeah? It's a quadratic function, so we can look at its discriminant. What's its discriminant? A squared minus 4b. Then we do the calculation. This is the discriminant, okay? Expression. C squared minus 4mk over m squared. Over m squared. All right. Then, based on the discriminant values, there are three cases. Case 1, the discriminant is greater than 0. Then you see in the discriminant c squared, c is the damping constant. C squared is greater than 4mk. That means the damping force relatively large because it's square larger than some constant. Okay, larger than that. Yeah, so we give a name of this system called over damping system. This case 1 is the over damping system because the damping coefficient is higher than some threshold. Yeah, there is some line. Okay, yeah, but it's higher than that. So over damping system. The second one, yeah. So here, in order to represent the second one, I use introduce two notations, alpha, beta. Yeah. Because if we use the original formula, it's too long. So here we use alpha, beta, so we can make the formula shorter. Yeah. Yeah. So we, with that notation. So for the case 1, we can write the general solution in this way. Is alpha, beta. Okay? Yeah. Yeah. Alpha, beta. All right. Then case 2, this time discriminant equals 0. 0. Yeah. Then we treat it as the line, the comparison, that line. So we give a name, call it critical damping. Yeah. The line, right at that line, that's critical line. Separate, different cases. So the critical damping. And its solution, general solution, can be represented in this way. Yeah. We just apply our old formulas. Yeah. We have all these formulas before. Okay? Yeah. Yeah. So in our part A, yeah. Module 2, part A, we have all these formulas. So here we just apply those formulas. Case 3, less than 0, discriminant, so we call it under damping type system. Yeah. And the general solution formula is like this, and here we use omega star because the star is slightly different from that omega 0, because remember there is I. We need to use I. We need to switch the sign, right? Because less than 0, we don't want to use, because if we take square root of this number, we get I. So we need to switch it. Take square 0, then there is no I. Okay? So the omega star, we want to remove that I. The reason we introduce the omega star notation, we want to eliminate I in the expression. This way, there is no I. Okay? Yeah. So omega star. Capital A, constant to be determined. Capital B, constant to be determined. Just like little c1, c2. Yeah. In general solution. Okay? Yeah. All right. So that's all three cases corresponding to the damped system. Damped system. Okay? Yeah. All right. Yeah. So we apply our formulas we derived from part A of module 2. We apply here. Yeah. So we solve this mass spring system. Part of it. Yeah. We have more. Okay. Here, you know, the relatively simple cases. Now, the first two simplest cases. Yeah. Yeah. Later we will see, you know, more complicated cases. All right, so let's take a break.